All right, sorry about that. Can you hear me now?
Yeah.
We can hear you.
When I tried to when I tried to share that, it like just crashed Zoom or something. Okay, so this is the voltage standing wave ratio, right? And this number tells us some information about the ratio of the amplitude of the waves traveling forward down the transmission line compared to the ratio of the waves traveling backwards down the transmission line. And so you can derive that using the expression for the from the reflection coefficient, the magnitude of it. So did anyone get a number for this?
I got 3.65.
Okay.
Did I?
Yeah, this one is if you have the reflection coefficient already, this one's fairly easy to calculate. And this is for a if you are connecting something, right? If you have a transmission line with a characteristic impedance and you are connecting it to a load like this, this is a fairly high voltage standing wave ratio. This means that when you have a wave, right, and it's traveling forward down here, and when it hits this load, it makes a pretty big reflection coming back. And that's usually not a very good thing, because the wave that's being reflected back, right, eventually on this side, right, you're going to have some other electronic equipment back here, probably some kind of a voltage generator or something. And if it's not protected well, this wave that's coming back can damage any electronics over here. So this is a somewhat high voltage standing wave ratio. Okay. Now, what about the position of the voltage maximum nearest the load? Did anyone finish that calculation? So this is asking, right? We have, like we just spoke about, we have the transmission line like this. And this is where the load starts. And so these two waves are going to combine, right? And so they're going to combine into something, I don't know, let's say like this. Right? And what we're wondering right now is, this is where the load is. This would be the maxima, right? This is the maximum voltage nearest the load. And so the next two questions are asking us about the position of the voltage maxima and the current maxima that's near the load. And so this is some distance that we're interested in. And we can see, right, that there's going to be many maximas that we could find. So there's the maximas will be repeating. And we can find the maximas as a function of the angle times the wavelength over 4 pi plus n times lambda divided by 2. Okay, so this is the first maxima. This is the second maxima. Oh, so this is the third maxima, and so on.
So that angle, is it still going to be in radians or will it be in degrees?
Let's see here. I think you are going to need to convert this back into radians for this to get this result. And our wavelength rate, this is 8 centimeters. I didn't even get an answer.
I got 3.11 centimeters.
Yeah, that is also what I got. Now, one thing that you should know is that there are two different ways also that you can look at this. Okay, so right, depending on the angle that you have here, right, this angle right describes the reflection coefficient, and the reflection coefficient is telling us, you know, how much is being reflected back from the load. So the reflection coefficient has two possibilities. One, right, you can have a reflection coefficient that is less than 0, or 2, you can have a reflection coefficient that is greater than or equal to 0. And this is essentially going to be shifting what the starting location of this wave is. And so this D max, you can write it in two ways, or another way that it can be written is this angle plus 2 pi n over, sorry, actually, let me write it. There's a number of ways you can write it, but this is, so we wrote it like this. And if this is less than 0, then the ends, you should start the numbering with 1, 2, 3. But if it is greater than 0, you should start the numbering of ends from 0, 1, 2, etc. Okay. And that is due to the movement of this wave where the reflection begins. And similarly, if we want to find the current maxima, right? So the current maxima occurs at voltage minimas. So the D min is equal to D max minus lambda by 4. So your minimas and maximas will be separated by this quarter wavelength. So we found a current maxima. And now we want to find we found the voltage maxima. And now we want to find the current, current maxima, and that will be related to the voltage minima. So if we want to find the voltage minima, we can take this distance where the maximum occurred and then subtract a quarter wavelength. And this has another similar situation where you subtract the quarter wavelength if the D max is greater than or equal to pi 4. But if your D max, which we found the D max is 3.11 centimeters. So if the D max is less than a quarter wavelength, then you would take the D max plus quarter lambda. Okay. So did our voltage maxima, is it larger than a quarter wavelength?
Yeah, it is.
Yeah, because this is Right, so our, yeah, so. Yeah, so we have this case. So what is the D min?
It'd be 1.11 centimeters.
All right, so any questions? And right, and that's because, right, our quarter wavelength, right, this is what, 4? Okay. So now I guess we have just a few more moments. So you can verify all of this using this module 2.4. So this tells you how to put everything in. It shows you the transmission line. So we had a characteristic impedance here. Let's see, I believe we can get the same result for any frequency. This is our input for the transmission line or the load impedance. So we had what, 30 minus J50 update. Okay. So let's see here. Our reflection coefficient, right? This is what we got, right? Does this look correct? 0.57, angle 79 degrees. That's what we got.
Yeah, that's correct.
Let's see. What else does this show? In the data 2, right? This is the standing wave ratio, S. So we got 3.66. So this is also what we got. Now, what if we move? Let's see. When we move D, right, we can see all of this stuff is changing. Oh yeah, okay, all right. We did have to update this. I think we needed to calculate. We may need to calculate this. Yeah. So actually, this should be 3.75 E9. Now we can move this around and we can set the line length higher if we'd like. We can do a variety of different things and move this around until we get to the point where we can check if we have the impedance or the voltage reaching a maxima or a minima here. Okay, so any questions? Let's see, I think this. So we can look at the voltage and current phasors here. And a whole bunch more stuff. Questions? All right, well, on Thursday, I'll have another quiz. So if you took the quiz today, you can take it again on Thursday for another chance. Hand in this homework on Thursday. If you want to revise, you can resubmit then also. So Stick around if you have any questions. I'm also going to send out a list of times available that you could meet with me to show me your generator project to have the status report meeting. So I'll ask you to sign up for those. So yeah, feel free to take off now. And if you have any questions, you can stick around.
Thank you.
Yep, you're welcome.
That,
So I might be going crazy, but has assignment 10 been posted on Moodle? Like the homework?
yeah, that's what I was gonna say is I don't
Yeah.
think you have that available to us.
Shoot. Okay. Yeah, I'm sorry. I don't think it's up either, but I will post that now.
All right, sweet,
All
thank you.
Yeah. Do either of you have your generator stuff done and want to meet this week?
Like I have the plans for it and everything, just not all of it put together.
Okay. Yeah, probably next. I just figured there might be one or two people who was interested in meeting this week, but some of the calculations, I don't know if people have looked into that yet. So probably after the break, I'm guessing people will be more interested.
Thank you.
Probably, yep. All right, well, thank you.
You're welcome. All right. Have a nice day.
Thanks, you too.